Okay, gang, this will probably be my last post before spring break, which is next week. By the way, next week I'll probably be answering emails, but I'm not going to post any new stuff for you to do. So if you still want to work on these assignments over spring break, that's fine, but I'm not going to put any new stuff up. Also, I should probably let you know that I plan on sort of giving you guys an update of what you're missing, what needs to be done, so that we can be able to settle up. I'm sure your inbox is just getting flooded with updates from Classroom and new comments and everything. So I just want to give you a sort of a one, like you can look on PowerSchool. So I hope to update that by the end of the week or maybe this weekend. So we did an example in the last video about figuring out what decibel level is given a certain intensity. So we worked out this previous example, and it came out to 92 decibels, which I didn't really give us. There's a couple comments I wanted to make, but I got cut off for time. So the reason that this is 92 decibels is it's like 10 to the ninth times as large. So this number is about a billion times as large as this one. And a billion is 10 to the ninth. So we know that log base 10 of 10 to the ninth should be around 9. Okay? And so it would be 9.2 bells. But since for some reason we like to do everything in decibels, it's got to be 92. So we multiply it by 10, just slide the decimal over one place. So that adds always sort of an extra step to our calculations to figure it out in decibels rather than in bells. So is 92 decibels even, is that loud? Like how loud is the trumpet? So if we look I'm going to move this to the side here. 92 decibels is, can I even scroll down on this page? 92 decibels would be about as loud as like a lawnmower. So this is really what most people say is around the level where it starts, you want to wear ear protection. If you were exposed to a noise level that loud all day long, you would have some hearing damage. So you'd have ringing in your ears at the end of the night and things like that. So really between 80 and 90 is really the loudest possible noise you want to be exposed to without wearing some hearing protection. And then you get to 100 decibels, 110, 120 is what they call the threshold of pain. This would be like I've heard different amounts for rock concerts and things like that. So 120 decibels would be like you're really causing immediate damage to your ears. So that's a trillion times the intensity of a regular, of the lowest possible noise. So let me do another example. I have two other examples I'd like to do, just getting us a better feel for relative intensity. So we did one where we were solving for intensity with this trumpet problem, and so I want to work on kind of another way. A normal conversation is 50 decibels. I'm going to turn another light on in my office here to make this a little bit easier to read too. Normal conversation is 50 decibels. How many times more intense is this sound than a human can perceive? Again, that's talking about that reference intensity. So there's a couple different ways to think about this. So one way, you could just kind of look at a chart and say, oh, we're going from 0 decibels is the lowest possible, and every time we go up 10, 20, 30, 40, 50, every time we go up 10 decibels, we're multiplying by 10 or removing the decimal place one more point over. So 0 decibels of 10 is 10 times, and then 100 times, 1,000, 10,000, 100,000. In other words, this has got to be 10 to the 5th times as loud as 0 decibels. That's one way of thinking about it. If you wanted to work it out mathematically, you could write it using the equation rearranged the other way. So where we said intensity is equal to I0 times 10 to the perceived, or to the decibel level, divided by 10. Okay, so 10 to that power. Okay, so you could work this out and say, okay, this has got to be I know that 10 to the 50 over 10 is the same thing as 10 to the 5, okay? Oh, that's really what we got going the other way. So it's 10 to the 5 times this reference intensity. So I don't even need to plug any numbers in here. I could have just done it by just adding tens, figuring out that way. Or I could figure it out by just saying, oh, it's got to be 10 to the 5. So really when we say 50 decibels, what we're really saying is 50 tenths as a power, which is 10 to the 5. So it's another couple ways of thinking about it. I'm trying to give you a bunch of different ways to think about it, and hopefully one of them kind of sticks. Okay, working out another problem that way, where we're trying to come up with an intensity given a decibel level. So I'm going to work out one more that way because there's another one like this in your homework. How powerful must a source be, the source of a noise, that is perceived as 55 decibels at 20 meters away? So 55 decibels at 20 meters away. Remember that distance isn't really part of your decibel equation, but it is part of the power equation. So this is going to be a two-step problem. We're going to have to first figure out what the intensity is, because going between decibels and intensity is really just a conversion one way or the other. And then I can solve using the distance to go backwards. I'm going to switch colors. I stole all my daughter's markers here. That's what we're using here. So first thing I want to figure out is the intensity, because that's kind of the go-between. So again, the intensity should be this reference intensity, I0, times 10 to the perceived volume, or the sound level, divided by 10. So remember, because these are always like tenths of a bell, so I got to divide by 10 in my equation. Okay, so my intensity from a 55 decibel noise is always going to be the same. Anytime you hear 55 decibels, that's always just a certain wattage that you're hearing. Okay, so that's 10 to the minus 12 times 10 to the 55 over 10. Okay, another way of writing this would be 10 to the minus 12 times 10 to the 5.5. So you should be able to, in your calculator, take 10 to the 5.5 power. So this is the same thing as, so 10 to the 5.5 power is like 3.2 or 320,000. This number is 10 to the 5.5. So if I multiply it all out, I end up getting the intensity is, oh, sorry, I'm looking at my camera. That was a bad move. I'm looking at the camera, not what I'm writing. So the intensity is 3.2 times 10 to the minus 7. And remember, the units for intensity are watts per square meter. Okay, so that's supposed to be a 7 there. Okay, so that doesn't tell me what the power is. Remember that power is, with the way that we solved for that, we said that intensity was power over 4 pi r squared, power over area. Okay, so I could rearrange this to solve for power by multiplying the intensity I just solved for by 4 pi r squared. I know from the problem here that my distance is 20 meters, or my radius of my sphere is 20 meters. So I'm going to work this out and say that power is going to be I times 4 pi r squared, and I know that r is 20 meters, and I know that I is this really tiny number of watts, 3.2 times 10 to the minus 7. Slide this over a little bit. Okay, and that's watts per square meter. Okay, and so you realize that this is going to work out pretty nice with units, because I'm going to square the distance, so square meters times watts per meter squared, I'm going to come back to watts as my unit. So power is going to be 3.2 times 10 to the minus 7 times 4 pi times 20 squared. Okay, so chugga in your calculator here, and it's going to come out to 0.0016 watts. So another way of writing that would be 1.6 times 10 to the minus 3 watts. Okay, so that's kind of one way. Here what we did, just to recap, we went from decibels, 55 decibels, we converted that to an intensity. So this is always just kind of a back and forth. You're always just using those same numbers to go back and forth. But you need a distance in order to figure out anything to do with power. So we had to have that given in the problem. So hopefully that was helpful in solving that. I'm going to post a few intensity and relative intensity problems to go along with your homework tonight. And I'll be leaving you alone until spring break.